begin by thanking Ajit and the other organizers for inviting me to this meeting and give me an opportunity to speak. It's indeed a pleasure to be back in this cool and calm ICTS. The detection of gravitational waves have clearly opened up a new window to the universe. In this talk, I will describe the manner in which non-trivial dynamics during the later stages of inflation or during the epoch of reheating, which is supposed to follow inflation, can lead to gravitational wave signatures which are comparable to the sensitivities of the various gravitational wave observatories. Later, I will very briefly describe the detection of the stochastic gravitational wave background by the pulsar timing arrays and discuss some certain very specific possible implications for the early universe. And time permitting, I'll briefly comment about non-Gaussianities and the roles it plays in determining the spectrum of gravitational waves. Here is a quick outline of my talk. I'll have some broad comments about primordial gravitational waves. And in this talk, I'll focus on what are known as primary and secondary gravitational waves. In particular, I will talk about what are known as scalar-induced secondary gravitational waves. And as I mentioned, if time permitting, I will talk about the impact of non-Gaussianities. I may have just one or two slides in this regard and close with a very broad outlook. Primordial gravitational waves are indeed a direct probe of the early universe. Over the last 50 years or so, the CMB observations of the anisotropies and the CMB has transformed our understanding of the universe. The CMB comes to us from about 400,000 years from the time of the Big Bang. It decouples from matter. The photons decouple from matter around this time of decoupling. And it is this last scattering surface that we are able to observe because of the fact that the CMB streams freely, virtually unaffected by the intervening matter. The gravitational waves are also weakly interacting, and therefore the gravitational waves that are generated either during this inflationary epoch, which corresponds to this rapid expansion of the universe, or due to secondary gravitational waves that can be generated during this epoch of radiation domination or during an epoch of reheating that succeeds inflation, can also travel virtually unaffected. There can be some small effects due to intervening matter, and which can be observed as a stochastic gravitational wave background today. And therefore, much like the CMB, they can tell us about the universe as it was during the earlier stages, but at considerably earlier epochs than the CMB. And of course, in contrast to astrophysical sources, the gravitational waves that are generated in the early universe can occur over a wide, significantly larger range of frequency. For instance, the primary gravitational waves I will talk about soon can occur, can have significant amplitudes over an extremely large range of frequencies from the CMB to the larger scales, much beyond even these terrestrial frequencies or frequencies much beyond these terrestrial interferometers. What are the primary gravitational waves? Well, these are perturbations generated from the quantum vacuum. Here is a quick picture of how the perturbations are generated during inflation. What has been plotted are two scales, the co-moving wave number, and this corresponds to decreasing wave lengths, or larger and larger k goes down. So you have the larger scales leave the Hubble radius. This is what is plotted in green is the co-moving Hubble radius, and it has a negative slope during inflation, and that is what allows you to have well-imposed initial conditions on the perturbations at early times, and that is what you impose on the gravitational waves as well. These are primary gravitational waves, are the gravitational waves generated from the quantum vacuum, and they evolve across, and they carry the imprints of the different epochs. You may have a primary reheating and then transition to a radiation domination. If you had instantaneous radiation domination, the slope would have been just +1 here roughly. You can have multiple epochs, where there is even a secondary reheating. For instance, the moduli field in string theory are supposed to dominate at a later stage after the original reheating has been achieved. And each of these will have different impacts on these primary gravitational waves. The primary gravitational waves, as Teeth already talked about, have some constraints from the CMB. This is on the larger scales at extremely small frequencies. We know the amplitude of the scalar perturbations very well. We do not know the amplitude of the tensor perturbations. We are trying to constrain the shape or the slope of the primordial spectrum, scalar power spectrum, and essentially the amplitude of the tensor perturbation, which is denoted as R, which is actually a ratio of the tensor perturbation to the scalar perturbations. And what you essentially find is that R is constrained to be about 0.036 or so. In terms of power spectra, it's about 10 power minus 11 or so. It's smaller than that. And this is on the larger scale. And what is the prospects? We are yet to observe the imprints of the primordial tensor perturbations. I should clarify, we are talking about primordial tensor perturbations generated from the vacuum. In addition, there can be tensor perturbations, secondary tensor perturbation during inflation itself. And these are also constrained by this, by such CMB observations. And what we have here are two plots for R about 5 times 10 power minus 2 and R of about 4 times 10 power minus 3, tensor to scalar ratio of these values. And these correspond to, say, these curves in red, blue, and green, and the black solid curve corresponds to the smaller value of R. And this is, instrumentation noise due to light bird, like for a light bird like configuration. So if you have R of 10 power minus 4, or 4 times 10 power minus 3 or so, you may be able to detect the primordial tensor perturbation through the so-called CMB modes, through over the coming decade or two, provided R is larger than that. But these tensor perturbations, well, if you have a tensor to scalar ratio of this value, say 10 power minus 3 or so, as I mentioned earlier, they evolve post-inflation and they carry imprints of these different epochs, and they are seen to us, we see them as a stochastic gravitational wave background, and they will have different, what has been plotted is the so-called dimensional spectral energy density, and I have plotted for different non-trivial scenarios. Here is a scenario where you have an epoch of reheating, which has an equation of state greater than 1/3, then it will have a positive slope, and it can be comparable to the sensitivity of the detectors, various detectors. You can have a more non-trivial scenario. You have a phase of reheating that immediately follows, which is matter-like, and then later there is a period of kination, which you can construct involving some simple scalar fields, and then what essentially happens is that the slope rises as fast as 1, and there can be scenarios which are again, comparable, which lead to primary gravitational waves, which are compared with gravitational waves, which are comparable to the sensitivities of the various gravitational wave detectors. Or you can turn it around and can talk about constraints of such scenarios from the various sensitivities. This is as far as the primary gravitational waves are concerned. This is gravitational waves, generated from the quantum vacuum, and they evolve across the various epochs to be seen as a stochastic gravitational wave background. But there can be other, sources of gravitational waves, secondary sources of gravitational wave. In fact, there are many, and I will talk about one particular one, which are known as scalar-induced secondary gravitational waves in light of Teruaki's talk. And this is related to the fact whether, primordial black holes could have formed in the early universe. The amplitude of the scalar perturbations very well from the CMB observations, and the dimensionless amplitude happens to be lies between 10 power minus 4 and 10 power minus 5. But if you want to generate significant number of black holes that FPVH close to 1, or even FPVH of 0.1, you need significantly higher amplitudes as far as the primordial perturbations are concerned. In fact, the amplitudes has to be very close to 1 if you want to have a sufficient number of primordial black holes. The constraints I talked about on the R and NS that earlier corresponds to constraints on what are known as slow roll inflationary models. But if you want to generate significant number of primordial black holes, you require deviations from slow roll inflation. And in fact, a particular type of model has been very popular in the literature. This is a typical inflationary potential. If you don't have this feature here, it would have just fallen, like this and gone down. But what happens is that if you introduce a point of inflection in the potential where you have the first and the second low roll parameters, the first and the second derivatives of potential vanish identically, there is such a regime here. What essentially happens is that this would have been the inflationary slow roll attractor. It wouldn't have the tilt. It would have been almost flat if you had a slow rolling potential. But because of this point of inflection, what essentially happens is that the velocity of the field decreases significantly, and this induces what is known as ultra slow roll inflation. The field is not just slowly rolling, it is rolling extremely small, and this leads to spectra of this form. This is a typical slow roll spectra, which is nearly scale invariant. This is the scalar amplitude, and this is the tensor amplitude. The tensor amplitude, as you can see, is about a couple of orders magnitude smaller than the scalar amplitude. But if you have an epoch of ultra slow roll in potential which contain a point of inflection, the amplitude of the perturbations on very small scales can be significantly high, and they can generate adequate number of primordial black holes. And there was a question about what is the mass of these black holes. It depends on where the peak in the primordial spectrum is, and you can shift that around, and there is reasonable freedom as far as inflationary models are concerned to generate adequate number of primordial black holes subject to the constraints that Teruaki showed, and at different masses as well. And this is not only in single field models, you can go to two field models of inflation where there is richer dynamics, and therefore you can play around, and what you can do is that you can generate a variety of curvature of a spectra or scalar perturbation spectra which have peaks, significant peaks at different wave numbers or frequencies, and these correspond to what are known as these names or the references correspond to the peaks in the secondary gravitational waves that I will talk about. At the leading order in the perturbations, the scalar and tensor perturbations evolve independently, and therefore you have constraints on the tensor to scalar ratio, and you have constraints on the scalar spectral index. But the higher order, once you take into account the higher order in the perturbations, second order scalar perturbations can induce tensor perturbations, and they can in principle dominate the first order tensor perturbations of primary gravitational waves. Let me illustrate that. So what has been done is that we have assumed that there is an instantaneous transition from the epoch of inflation to reheating. There is a sharp peak in the power spectrum, like I illustrated in the previous slides, and calculated what is the secondary spectrum of gravitational waves that have been generated. And what you find is as follows: if you had only slow roll inflation, the secondary spectrum of gravitational waves would have been somewhere here. The primary spectrum, if you recall the plot that I had earlier, where it was at about 10 power minus 17 or 10 power minus 18 in this units of omega GW h squared. But the secondary spectrum would have been something like 10 power minus 23, 24 or so. But because the scalars are inducing the secondary spectrum, and the scalars have a significant amplitude, you can have a rise in the secondary spectrum of gravitational waves. And again, you can tweak the, as I mentioned in the previous slide, I can move these peaks around. How do I move the peak around? I change the inflationary dynamics. There is sufficient room, and I can have the peaks at different locations, and I can generate spectra with different amplitudes. Here is in a single field model permitting what is known as ultra slow roll inflation. Here is in a second, in the two field model, and I can have secondary gravitational wave generated at different frequencies, and evidently the peaks are comparable to the sensitivities of the different gravitational wave observatories. In principle, these could have been seen by SKA, as I will talk about a couple of slides later. There can be more complicated dynamics. I should emphasize, I'm talking about only one type of secondary gravitational waves. Magnetic fields, for instance, can be generating secondary gravitational waves. Phase transitions of the first order can generate gravitational waves. There are many, many mechanisms. I'm focusing on one of them. And I should also mention there can be more complicated mechanism at play. For instance, you can have a scenario which Rajiv, for instance, has examined. You have a collection of black holes, primordial black holes that have been produced, and they are dominating the expansion of the universe for a certain period. And they, in turn, induce additional isocurvature perturbations. And in addition to the primary peak, they can induce a secondary peak as well. So there are many, many mechanisms that can play a role in this process and leading to gravitational waves of different amplitudes. Now, in the next minute or two that I have, I will talk about the PTA observations. Well, what has been plotted here is the base factor for different models, when one compares models with the data as far as the PTA observations are concerned. And what one finds is that this SIGW, scalar induced gravitational waves of a Gaussian shape, seem to fit the data fairly well. And you can try to ask whether you can produce, secondary gravitational waves in a model of inflation, and which are consistent with the constraints on FPBH bounds that Thiruaki showed and fit the data fairly well. And in the inflationary context, that if you have strong departures from slow roll, it will lead to large non-Gaussianities. And in fact, what you find is that this is the scalar bispectrum, dimensionless scalar bispectrum. It has a shape very similar to the shape of the power spectrum itself. And you see the bispectrum itself has an amplitude close to unity, and they in turn can contribute additionally to the non-Gaussianities. And what essentially happens is that it can shift either way, depending on the non-Gaussianity can be positive or negative. The bispectrum need not be positive definite, and it can change the predictions for the secondary gravitational waves. And that will be my last slide. So let me just close with a quick outlook. The B mode, detection of the B mode polarization is important because it will allow us to determine the energy scale of inflation. The PTAs offer a unique opportunity to decode physics operating over a wider range of scales in the early universe. And of course, forthcoming observatories will provide additional constraint on primordial gravitational waves. Thank you very much for your attention.
Thank you very much, Sriram. It's a very comprehensive overview. We have time for a couple of questions.
Thank you for the talk. On one of your early slides, you showed the power spectrum coming from reheating models with sort of the ability to rise at high frequencies. Can you put that back?
Yes.
That was one of the earlier slides.
This one first.
No, I want you to go back further. Just the effects of reheating. You had
yes. This one.
Right. So in the traditional pictures of reheating, a scalar field rolls around at the bottom of the potential, producing radiation. And there's a characteristic oscillation frequency as it rolls back and forth. And so I would have expected that the effects of reheating would have just been a peak at that frequency, suitably redshifted. So can you explain why it is that you have these rising spectra?
What's happening is that we are considering where we are, this has been, those transitions have been smoothed over. We are assuming that there is a instantaneous transition from, say, inflation to a WRE-dominated epoch of reheating in this picture. If you have oscillations, they leave small signals like that here.
Okay. So what's giving rise then to this rise?
Why is that rising? It's rising because the potential, if it will, for WRE, an effective equation of state, which is, or in other words, the potential, if it is greater than 5.4, then you can have a tilt, which is greater than unity, which is a positive tilt. That is, if during reheating, if the equation of state is greater than 1/3, then it induces, here is the tilt.
Okay, thank you.
You're asking about this rise. Okay.
Yeah, I had a question regarding the base factors. The base factors that you showed.
PTA.
In the PTA data. Are you saying that the scalar induced GW?
The next one, right? The next.
This one,
yeah.
yes.
Are you saying that the scalar induced GW model is preferred over the standard astrophysical interpretation of merging supermassive black hole stochastic background?
So I can have a scenario. One of the issues that, yes, that is the bottom line. Okay. So there is significant freedom in constructing spectra which fit the data well, and allowing them to re-enter, allowing those modes of interest to re-enter during reheating gives me one more parameter as well. So it is, I think, this particular curve with what is called as R2PB, the dashed line, one of these two curves fit the data fairly well. In fact, if I use PTA arcade, I find base factors of 300 or something like that. Okay, so we have just taken this, compared with the data, and we find that it fits the data fairly well. So, sure.
This base factor is usually a ratio?
Sorry?
Base factor is usually a ratio kind of thing. So this is with respect
to the
circular orbit.
Yes, that's right. Yes.
Just want to.
Yes. So, yes. But if you tweak that, we need to tell me how you are going to tweak that, and then I can compare the base factor.
Okay, thank you, Sriram, for this very nice talk. And let's thank all the speakers of the session as well.